All right, this is where we stopped last time. Unfortunately, I wasn't sure whether this was recording or not, so I had to stop it. Let's go back to what we got last in the last segment. We uh, we wrote a reduced equation of motion. Reduced equation of motion, and at the global level, this is at the global level. I have a mass matrix times a global acceleration vector plus a stiffness matrix times a global displacement vector equal to some kind of a global load vector, something like this. Okay, this is the global load vector. I already mentioned that the mass matrix is symmetric. Both M and K, mass and stiffness matrix, are symmetric and sparse. In the case of tetrahedral element or solid elements that you have in CATIA, for example, these matrices, the element matrices are very large, and then when you have thousands of elements, the size of these matrices can be extremely large. For example, I don't know, it could be of the order of 100,000 by 100,000. Now, in your course 85-220, numerical analysis, you were exposed to the process behind solving a system of differential equations. In other words, these are differential equations. These are differential equations that have to be integrated numerically in time. And this is not an easy task, but there are software and there are techniques for doing this thing. And at the end of the day, the information that you're going to get is something like this. You're going to get, as a function of time, once initial conditions are specified. You cannot integrate this thing unless you have some initial condition or given. Okay? But once you have the initial conditions, you can integrate these in time, and at the end, you're going to get a curve like this. This could be x2 as a function of time, perhaps a curve like that, I don't know, x3 of t, and maybe a curve like this, x4 of t. Now, when you get x2, x3, and x4, you can go to the first row and the last row of the system of equation that we discarded. Once you have x2, x3, and x4 completely, go to the first and the last equations of your global system. Remember, the first and the last row involve the reaction forces of the wall. So if you go back there, you can plug in your information and find reaction force at the left wall and reaction force at the right wall, and you're going to get, you can find these. Now, I'm not going to write it down. You can go and write the expression for R1. You see that it involves x1, x2, x3, x4, x1 double dot, x2 double dot, etc. But you have all that information. Plug in and you get your reaction forces. Now, I would like to make some other comments about this thing, this process. Now, notice that I labeled I labeled the elements consecutively like this. And these are the masses. Okay, one there, another one. So I labeled this thing as node number one, node number two, element number one, element number two, element number three, and four. And this being node number one, node number two, node number three, node number four, and node number five. It doesn't have to be like this. You can pretty much randomly label the elements and the nodes, but the numbering, the labeling, numbering of elements and nodes affect the bandwidth of your mass matrix and your stiffness matrix. In the old days, when I say the old days, I'm talking about perhaps, I don't know, 30 years ago, 40 years ago, people actually had to sit down and even in it, first of all, you could not do very complicated problem. And even then, people had to decide on how to label the nodes and the elements so that it gave you minimum bandwidth. You know, gradually with the advancement of computers and algorithms and things like that, these are done internally and without any user interaction. Like you never worry about how to element in CATIA, how to when you break it up into elements, the 3D object into element, CATIA internally does it so that these things are optimized. Now remember, we can very routinely, even the problems that we're solving in class today, these days, with CATIA, they may involve 30,000 matrices of order 3,000, but 30,000 by 30,000. This is nothing, okay? But storing a 30,000 by 30,000 matrix, let alone the calculation, forget about the calculation, is not going to be easy in a computer. And this is nothing. I mean, there are in finite element problems, there are matrices. If you were to do it the way I described it, of order 10 million by 10 million, it's not going to fit. Doesn't matter how much disk space, you know, how much RAM you've got and things like that. You won't be able to store matrices of this size. So there are a lot of mathematical, you know, scenery behind all these things. How do you store huge matrices? How do you manipulate huge matrices? These are not easy problems. They involve a lot of knowledge of computer science, knowledge of mathematics. But I can tell you the people who came up with these ideas were originally engineers. And this is why do not get the impression that taking 5 math classes is going to be good for many of you. If you decide to go to graduate school at big universities, uh, you're going to need a hell of a lot of math before you can even understand, before you can even uh, attend lectures. Okay? Engineering is important, good, but I do see the attitude that this is all math, I don't have to know it. Well, you're dead wrong. All right, let's go back to. I don't want to give you a lecture on this. Let's go on and continue with this thing. All right, uh, let me go and insert the page here. Okay. Now, so at the end of the day, even if we don't know how it's done, you have a huge system of differential equations to solve. Like so. Of course, you need initial conditions, and you need initial condition, maybe position and acceleration, or position and velocity before you can actually solve this thing, integrate in time. But my point is that if the inertia term, inertia term is the mass times acceleration term. In other words, if this is small compared to the other terms, when I say the other terms means that kx and f, for example, then maybe we can drop it. We can ignore it. In other words, the equation that we're going to solve is going to be this. Okay? And this is what we call a static problem. A static problem. I don't want you to get the impression that dynamic means there is time and static means there is no time. Dynamic means the mass times acceleration is important. You have to keep it, and you have to integrate this in time, and pretty much it. Static problem means the mass times acceleration is small compared, or the inertia term is small. You can drop it, and you can solve a matrix equation. No integration involved. Again, we brought this up in the lab a few weeks ago. I asked, what is the definition of static? What is the definition of dynamic? And somebody said, I remember his face, he answers good questions. He said that static means there is no time, and dynamic means there is time. And I said, that is not true. Everything has time in it. Everything. When you say you apply a load of 50 pounds, that 50 pounds was not created by the the higher authorities. The 50 pounds start at 0 pound, and you build it up to 50 pounds by maybe pressing on it or pushing on it, etc. That does not mean that this has to be solved as a dynamic problem. Okay? We will come to this issue of static versus dynamic in a few weeks once I talk about natural frequencies or frequencies of vibrations and things like that. Now, in CATIA, we can solve both static and dynamic problems. However, for now, we are concentrating on static problem. In other words, CATIA gets you this huge matrix equation, and it will solve it for you, and this is what displays on the screen. It is possible to do dynamic problems in CATIA too, but let's not worry about it right now. Now, I want to do another example, and this new example is that I'm going to label the nodes differently and the elements differently in a random way. And then we try to get the stiffness matrix and guess the mass matrix and solve the problem. Let me go down here and take exactly the same problem that you were doing before. Okay? So we just did, in other words, exactly the same problem. Different numbering. All right. Actually, you know what? I'm going to make it a slightly different. Well, all right. Let's do the same one. Okay, there. We had 4 springs and 3 masses. There we are. This is stiffness K1, K2, K3. Wait a minute. K1. I'll call this thing element 4. So it's going to be element 1. This is element 4. This one is element 2. So K2. And this one element 3. And this is K3. And the nodes I'm going to label like this. This one is node 1. At the very, the next one is going to be node 3. Next one is going to be node 5. And node 4. And node 2. Okay? I kind of randomly label these things. Now, what do we want to call this thing? This is going to be our M3 then. This is going to be our M5, whatever it happens to be. If it's 5 kilogram, 10 kilogram, whatever. And this one is going to be node mass 4. All right. One thing we know is that there are still 5 degrees of freedom. And those are X1, X2, X3, X4, and X5. However, X2 is 0 and X1 is 0. So at the end of the day, we have to solve for X3, X4, X5 in time. And the reaction forces, reactions are R1, unknown, and R2, unknown. Okay, good. All right, move on. So for sure, when we write the global equation, we're going to get a 5 by 5 mass matrix, a 5 by 1 acceleration vector, a 5 by 5 stiffness matrix. I'll write this thing as big X. Stiffness matrix, again 5 by 5. A 5 by 1 displacement vector, and a load vector which is also 5 by 1. However, the structure of these matrices, as you will see, and that is the purpose of this this particular way of doing it, is going to be different. There's still going to be banded. There's still going to be a lot of zeros, and they're going to be symmetric. However, they will not be the same matrices that you saw before. But once you solve it, the information that you get obviously must be the same as the information that you got solving any other way, because this is a physical problem. So we still have to loop through the elements okay, loop through the elements. So element number 1, the generic element number 1, just like before. I don't even have to draw these things, but it's helpful, at least initially, if you see them. So this is element number 1. There's always a left endpoint, left mass. There's always a right mass. There's always a left force and a right force, a displacement XL, and a displacement XR. Okay? All right. So the equation of motion for this element is going to be ML. I put a 1 here because this is coming from element number 1. MR, put a 1 there, times XL double dot, XR double dot, plus the stiffness, minus K1, minus K1, K1, times displacement, XL and XR, equal to FL and FR from element number 1. That's why I put a superscript 1 on top of that. Now the question is, where is this thing going to go? When I try to put it in my mass matrix, in my equation of motion, where is this going to go? So let me go and get one of those global things and bring it out here. Okay, be patient, please. Okay, so let's see now. And paste. Right. Okay. I'll move this thing down. All right. Where is this? Oh. You know what? Let me stop here. This is going berserk. I'm gonna stop here and go in the next segment and work this out. Okay? Really sorry. This software is not very good, and that's all I can say.